Welcome to the Deep Dive, where we plunge into the heart of fascinating ideas and emerge with the clarity you need. It's always inspiring to hear the stories of legendary explorers, isn't it?
Oh, yeah, absolutely. The ones who push the boundary.
Exactly, capturing our imagination. But, after the heroic return, there's this other crucial group, the cartographers.
The map makers, often overlooked.
Totally unsung heroes,
Yeah.
meticulously mapping out the new terrain so the rest of us could actually navigate it. And today, we're kind of taking on that cartographer's role for you, our listener. We're providing a map of some, honestly, incredibly complex intellectual terrain, specifically where science, philosophy, and religious belief intersect.
It's a landscape full of surprising connections, often overlooked, I think. Many people tend to assume these fields are either in constant conflict or maybe entirely separate domains.
Right, like never the twain shall meet.
But the reality, as we'll definitely see, is far more nuanced than that. Much more interesting, actually.
Absolutely. Now, our mission today is to extract the most important nuggets of knowledge and insight from a truly rich source. The Physics of Theism, God, Physics, and the Philosophy of Science by Jeffrey Koperski.
It's a dense book, packed with ideas.
It really is. So this deep dive is basically your shortcut to being well-informed on these fascinating, and let's face it, often pretty heavily debated topics. Okay, let's unpack this.
Let's do it.
So we're starting with cosmology, and specifically the Big Bang. Now, the idea of a universe with a finite past, which came out of those early cosmological models, the ones leading to what we now call the Big Bang, that caused quite a stir, didn't it?
Oh, it really did. A huge ripple effect across different communities.
How so?
Well, for many theists, it was seen as a powerful confirmation of creation ex nihilo, creation out of nothing. Pope Pius XII, for instance, publicly expressed his approval pretty early on. And there's that evocative quote from astronomer Robert Jastrow, who was himself an agnostic, by the way. He said, "For the scientist who has lived by his faith in the power of reason, the story ends like a bad dream.
Go on.
He has scaled the mountains of ignorance. He is about to conquer the highest peak. As he pulls himself over the final rock, he is greeted by a band of theologians who have been sitting there for centuries."
Oh, wow. What an image. That really paints a picture. But as you might expect, the reaction from the atheist community was, well, quite different.
Indeed. Very different. Physicist William Bonner, for example, viewed the Big Bang as, and I quote, "a religious doctrine masquerading as science." He felt it was theology sort of opportunistically reasserting itself.
And Fred Hoyle, he actually coined the term Big Bang, didn't he? But not as a compliment.
Not at all. He meant it pejoratively, dismissively. He called it a form of religious fundamentalism. This kind of skepticism, this resistance, it really fueled the search for alternative models.
Like the steady state model.
Exactly. That was the most prominent one. It proposed an infinitely old universe where matter was being continually created to maintain a constant density as the universe expanded. No beginning point.
And some saw that as a direct challenge to a creator.
Yeah, Carl Sagan, for instance, argued that the steady state model, if proven true, could actually disprove a creator.
So what's crystal clear from these reactions is that right from the start, these big scientific ideas weren't just happening in a vacuum. They were deeply tangled up with philosophical and, religious implications.
Absolutely. Intertwined from the get-go.
And this leads us to a really crucial piece of our map, doesn't it? Because the conventional wisdom often frames science and religion as either locked in conflict.
Right, the warfare model.
Or as completely separate, non-overlapping realms. But Koperski, our source, argues both views are, deeply flawed. Why is that?
Because the relationship is just far more subtle and frankly more complex than those simple narratives allow. It's not black and white.
So how do we get a better handle on it?
One key concept Koperski introduces is meta-theoretic shaping principles, or MSPs.
MSPs.
Yeah. Think of these as the underlying views about the physical world and how we should study it. They're almost like unconscious assumptions that shape how science gets done.
Like the ground rules everyone just accepts?
Pretty much. They're rarely noticed because they're often seen as just, the way things are scientifically. But here's the surprising part. Religious beliefs have actually played a pretty significant role in their development, especially since the scientific revolution.
That is surprising. So let's dig into that history a bit. It seems foundational to how we even think about science today. We usually trace the roots back to ancient Greece, right? Plato had his ideas.
Right. Plato and his forms, that invisible, timeless, ultimate reality with our world as just an imperfect copy. Knowledge came through insight beyond the senses.
But our source points more to Aristotle's being really influential for early modern science.
Yes, much more so, particularly in the medieval period leading up to the Revolution. Aristotle, unlike Plato, thought the essence of things was in them. He talked about hylomorphic composition.
Hylomorphic.
Okay, what's that? It's the idea that everything is made of prime matter and an essence or a substantial form. So take a falling stone. It doesn't need an external force pushing it down.
It just falls because it's a stone.
Exactly. It falls because it's part of its essence to move towards the center of the earth. That was its natural place. This whole way of thinking meant that natural philosophy, the precursor to science, focused on abstracting these universal essences through insight, not really through empirical observation.
And that led to a very different approach to knowledge, didn't it? Where experimentation wasn't really the focus.
Not at all. In fact, artificial experiments were often seen as producing violent behavior, something contrary to an object's true nature, interfering, basically.
So you wouldn't learn about the stoneness of a stone by, say, chipping away at it.
Precisely. You'd be disrupting its nature, not revealing it. So for centuries, studying Aristotle in universities often was what passed for science, rather than going out and actually looking closely at the world.
But things started to shift. People began critiquing these substantial forms.
Yeah, some thinkers started seeing them as occult entities, sort of hidden, mysterious properties that didn't really explain anything.
Like that Molière example for opium.
Exactly! The virtus dormitiva. Saying opium makes you sleep because it has a sleep-inducing power. It's circular. It doesn't actually explain how.
Right, it just redescribes the effect.
So this critique, along with the rise of nominalism figures like Occam, Abelard started changing things. Nominalists argued that essences were just mental concepts, labels we use, not independently existing realities.
And that put more emphasis on observing actual things.
Yes, it shifted the focus towards observation for understanding particular individual things, even if that knowledge was maybe seen as less certain than the knowledge of universals Aristotle aimed for.
And this philosophical shift was tangled up with theology too, particularly an idea called voluntarism.
Deeply intertwined. Voluntarism was the belief that God's choices in creation were contingent. God wasn't bound by some pre-existing eternal forms or a rigid rational necessity. God could have chosen differently.
So God wasn't just enacting eternal blueprints.
Exactly. Robert Boyle, a key figure in the scientific revolution, put it this way. Laws of motion did not necessarily spring from the nature of matter, but depended on the will of the divine author of things.
Okay, and the implication of that is huge for science.
It's profound. If God could have chosen different laws, if the laws aren't inherently necessary, then you can't discover them just by sitting in your armchair and reasoning about essences.
You have to actually look.
You have to go out and observe the world to see what choices God actually made. You need empirical investigation.
Now, it's worth noting, as the book does, that this didn't always lead straight to empiricism. Descartes is the counterexample.
Right. Descartes was a voluntarist, but he still relied heavily on pure reason and what he called clear and distinct ideas, which he believed were guaranteed by God. So it wasn't a direct one-to-one link.
But for many others, like Boyle and Newton.
For them, yes, voluntarism strongly implied that scientific truths needed empirical grounding. It pushed them towards observation and experiment.
Okay, and speaking of observation and challenging old ideas, we absolutely have to talk about the Galileo affair. It's always held up as the ultimate battle. Science versus religion.
The classic showdown narrative.
But Koperski, drawing on historians, argues that's a massive oversimplification.
It really is. Historians like John Hedley Brooke argue it wasn't a simple science versus religion clash at all. Brooke says much of the conflict ostensibly between science and religion turns out to have been between new science and the old sanctified science of the previous generation.
So it was new science versus the church's accepted science, which was largely Aristotelian.
Precisely. The church at that specific time was heavily invested in Aristotelian philosophy, which Galileo's observations, especially with the telescope, were directly challenging.
And it wasn't just about the scientific ideas themselves, was it? There was a lot of politics involved.
Oh, absolutely. It was very much about political authority. Koperski quotes historians saying it was primarily a dispute about the enduring political question of who was authorized to produce and disseminate knowledge.
Meaning the church felt its authority was being undermined.
Yes, and crucially, they couldn't afford to have a prominent scientist like Galileo making arguments that could potentially be picked up and used by the Protestant opposition. That was a huge political threat during the Counter-Reformation.
So the neat stories, science heroically liberating itself from dogma, or Christianity being the sole engine of modern science, they're just too simple.
Historians reject both as oversimplifications. Religious beliefs definitely shaped those metatheoretic shaping principles we talked about. Sometimes they hindered progress, like clinging to Aristotelianism or, later, young Earth catastrophism.
But sometimes they motivated it.
Yes, ideas like the rationality of nature stemming from a rational creator were powerful motivators for people like Newton. It's a complex interplay.
Okay, so having charted some of those historical currents, let's now turn our cartographer's compass to one of the most, well, compelling and current landscapes on this map.
Yeah.
The apparent fine-tuning of our universe.
Right, this is a big one.
It refers to the seemingly, impossibly precise values of fundamental physical constants, the basic numbers that govern physics, that allow life, as we know it, to exist. It really feels like we won some kind of cosmic lottery against unbelievable odds.
The examples Koperski cites are indeed striking, almost unnerving in their precision. Take the nuclear weak force.
Okay.
If it were just, say, 30 times weaker than it is, the early universe would have produced way too much helium, leaving much less hydrogen for stars and water. But if it were slightly stronger, no supernovae.
And without supernovae.
No dispersal of heavy elements like carbon and oxygen throughout the cosmos, elements absolutely essential for life, gone.
And it gets even more precise than that, right?
Yeah.
With the other forces.
Oh, yeah. The nuclear strong force, the one holding atomic nuclei together, a tiny change, just 0.4% stronger or weaker, would, quote, destroy almost all carbon or almost all oxygen produced in stars.
Both vital. You need both.
Absolutely. Or the electromagnetic force, make it just 4% weaker, no stable hydrogen atoms, no water.
And then there's the cosmological constant, the one governing the expansion of the universe.
That one is maybe the most mind-boggling. Its value cannot vary by more than 1 part in 10 to the power of 53.
10 with 53 zeros after it.
That's the one. Any more variation, and either the universe expands too fast for galaxies to form, or it collapses back on itself in a big crunch before life could ever get started.
The numbers are just staggering. Koperski mentions physicist Lee Smolin's estimate.
Right. Smolin estimated the chance of stars existing, just considering the range of these constants, is about 1 in 10 to the power of 229.
1 in 10 to the 229. How do you even wrap your head around odds like that? It's like winning the lottery. What did the book say? 10 times in a row.
Something like that, yeah. It highlights just how specific, how apparently lucky the circumstances of our universe seem to be.
It really makes you pause. But as you can imagine, this whole fine-tuning argument for, say, a designer faces some pretty significant philosophical hurdles.
It certainly does. One of the most common objections is the observational selection effect. It's often illustrated with what philosopher Elliot Sober called Sober's net.
Okay, tell us about the net.
Imagine you're fishing, but your net only has 10-inch holes. So naturally, every fish you catch is over 10 inches long.
Right, because the little ones slip through.
Exactly. So can you conclude from your catch that all fish in the lake are over 10 inches? No. Your observation method, your net, pre-selects the outcome.
So the analogy is we can only observe a universe capable of producing observers like us.
That's the argument. Since we couldn't exist in a life-prohibiting universe, the fact that we find ourselves in a life-permitting one doesn't, according to this critique, confirm intelligent design over random chance any more than the fisherman's catch tells him about the small fish. It gets into tricky philosophical waters around what's called the problem of old evidence.
Old evidence.
Yeah, like, should evidence we already knew existed, like we exist, before we even thought of the design hypothesis, actually count as strong confirmation for it? It's a point of debate in probability theory.
Okay, that's one hurdle. And it gets even more complicated mathematically with what's called the no-measure problem. This sounds like it's about defining probability itself.
Precisely. If the possible range of values for these physical constants is infinite, which it might well be, then assigning a meaningful probability to the tiny, tiny sliver that permits life becomes mathematically problematic.
So.
In an infinite space, any finite range technically has a measure of 0. So the probability of hitting that exact life-permitting range randomly is 0. Which is weird, because usually if something with 0 probability happens, that screams out for an explanation.
It seems counterintuitive.
It is. And this issue also affects the idea of course tuning. Maybe life could exist across a much wider range than we think. But even if that range is vast, If the total parameter space is infinite, that vast range still has a measure of 0. Mathematically, fine-tuning and coarse tuning can end up looking the same in terms of probability.
So if the math seems to hit a wall with infinities and 0 probabilities, how do physicists actually deal with this in practice? They still talk about fine-tuning needing explanation.
They do. Often they find practical workarounds. A common one is just to, truncate the range, assume the possible values aren't truly infinite, but just incredibly large and finite. That allows probabilities to be defined, even if it feels a bit arbitrary.
So kind of setting boundaries for the sake of calculation.
Kind of. Mathematicians might object to the lack of absolute rigor, but physicists often use inferential principles that work practically, even if they aren't perfectly watertight mathematically. Koperski makes the point that inferences about what does and does not need an explanation can be made on spaces of infinite measure, using these sorts of methods.
Okay, so even with these incredibly precise numbers, there are definitely philosophical and mathematical complexities for the fine-tuning argument. What are some of the major scientific explanations proposed to account for this apparent precision without needing an intelligent designer?
Well, one area physicists look to is more fundamental physics, hoping a deeper theory might explain why the constants have the values they do. Supersymmetry was a big hope for a while.
Supersymmetry, that's about unifying forces, right?
Yes, it's a theoretical framework proposing a symmetry between different types of fundamental particles. The hope was it might constrain the values of constants or show relationships between them, reducing the apparent fine-tuning.
Did it work?
Not really, or at least not yet. While it might explain some fine-tuning relationships, the problem is supersymmetry often introduces more new parameters that themselves seem to require fine-tuning.
So it just pushes the problem around.
That's often the case. As physicist Lee Smolin puts it, fine-tuning is easy to displace but hard to eliminate. Despite decades of searching for a theory of everything, no fundamental theory has yet successfully predicted or explained the specific values of elementary particle masses or the strengths of the forces. They still have to be put in by hand, essentially.
Which brings us to maybe the most talked about alternative explanation, the multiverse.
Yes, the idea that our universe isn't the only one. That it's just one bubble, maybe, in a vast cosmic ocean of universes.
And there are different flavors of this idea.
Quite a few. Koperski discusses serial multiverse models first. These are ideas like the ekpyrotic model involving colliding branes or dimensions, or Roger Penrose's conformal cyclic cosmology, CCC, where the universe goes through cycles or eons.
What's the big challenge for those cyclical models?
A major one is entropy, the universe's tendency towards disorder. For a new Big Bang cycle to start, the universe somehow needs to reset itself back to a highly ordered low-entropy state. That's thermodynamically very difficult. Penrose has a proposal involving black holes consuming entropy over vast timescales, but it's, let's say, not widely accepted yet.
Okay, so serial universes have issues. What about the other main the idea of many universes existing simultaneously?
This is probably more popular currently, often linked to the theory of eternal inflation, pioneered by people like André Linde. The idea here is that our observable universe is just one domain or pocket universe within a much larger, eternally inflating space-time.
And how do different constants arise in these domains?
Through quantum fluctuations. As new domains bubble off or inflate, tiny random quantum fluctuations in the underlying energy fields could cause the laws and constants of physics to settle into different values in each domain.
So, in this vast multiverse, universes with all sorts of constants would exist, and we just happen to be in one where the constants allow life.
That's the core idea. It explains fine-tuning by saying it's not fine-tuning for us, it's just that we could only exist in a region that happened to have the right numbers by chance, out of an enormous, possibly infinite number of possibilities.
But the multiverse idea, attractive as it might be to some, faces its own set of serious problems, doesn't it? Beyond just being incredibly hard, maybe impossible to test directly.
It definitely does. One issue is what Koperski calls the promissory note problem. Like supersymmetry, it often just pushes the fine-tuning problem up a level.
How so?
Well, for eternal inflation to work and generate all these diverse universes, the underlying mechanism, the inflating field itself, often needs to have very specific fine-tuned properties to begin with, including starting in an extremely low entropy state. So you haven't eliminated fine-tuning, you've just relocated it.
And that measure problem we talked about with infinite possibilities comes back too.
Big time. If there are infinitely many universes, how do you even define probabilities? How do you compare the number of life-permitting universes to life-prohibiting ones if both numbers are infinite? It's a mathematical quagmire that cosmologists are actively wrestling with.
And then there's perhaps the most bizarre and frankly unsettling implication for many, the Boltzmann brain problem.
Yes. This one is truly weird. The argument goes like this. In an infinite, randomly fluctuating multiverse that exists for an incredibly long time, simple things are statistically much more likely to pop into existence via random fluctuations than complex things.
Okay.
So, a single, isolated, disembodied brain that momentarily fluctuates into existence with false memories of a past and perceptions of a universe, a Boltzmann brain, is actually calculated to be overwhelmingly more probable than the spontaneous formation of an entire, complex, highly ordered universe like the one we seem to inhabit, complete with billions of conscious observers.
Wait, so statistically it's more likely that I'm just a random brain hallucinating all this?
According to the standard calculations in many infinite multiverse models, yes. Koperski puts it bluntly. Odds are that you are one of them. Sorry. It's a deeply problematic conclusion because it seems to undermine the very possibility of doing science if we can't trust our observations.
Gives you something to think about, indeed. Does this problem affect all cosmological models?
It seems to be a particular thorn in the side for infinite multiverse theories. Calculations suggest Boltzmann brains are far less probable in a single, finite universe like the standard Big Bang model. So it counts as a significant mark against many multiverse proposals.
That's fascinating. So Koperski suggests the multiverse isn't just a scientific hypothesis, but maybe reflects a deeper philosophical commitment, like that principle of indifference you mentioned earlier.
He raises that question, yes. The principle of indifference is one of those meta-theoretic shaping principles. The idea that our own circumstances, our time, our place, our universe's constants, shouldn't be special. They should be generic, typical.
And the multiverse provides a way to make our seemingly special constants look typical, because all possibilities are realized somewhere.
Exactly. It's a way to uphold that principle. Koperski suggests the multiverse might be seen less as a direct scientific inference and more as a metaphysical posit, a philosophical assumption made to preserve that underlying MSP, even when direct empirical evidence is lacking. It highlights just how fuzzy the boundary between science and metaphysics can sometimes be.
That's a really powerful lens.
Yeah.
Okay, shifting gears slightly, but still thinking about the universe being governed by laws. This inevitably brings up one of the oldest philosophical anxieties. Our own free will. If everything follows physical laws, where's the room for choice?
Right. This has been a challenge since Newton, really. If every particle, including the particles in your brain and body, follows deterministic laws, then isn't every action, every thought predetermined? The kicker doesn't choose to kick the field goal. The initial state of the universe plus the laws necessitated it.
And Einstein's theory of relativity seemed to deepen this challenge, pushing towards this idea of a block universe. Can you walk us through relative simultaneity again, the train example?
Sure. Imagine Marcus is on a fast-moving train right in the middle of a carriage. He sets off a frish bulb. From his perspective, sitting on the train, the light reaches the front and back walls of the carriage at the exact same instant. Simultaneous.
Makes sense.
Okay, but now imagine Andrew is standing still on the ground, watching the train whiz past. As the light travels from the flashbulb, the back wall of the train is moving towards the light pulse, while the front wall is moving away from it.
So from Andrew's perspective.
From Andrew's perspective, the light hits the back wall first, and then a fraction of a second later, it hits the front wall. They are not simultaneous for Andrew.
So what's simultaneous depends on your frame of reference, how you're moving.
Exactly. And the profound consequence of this, according to the standard interpretation of special relativity, is that there can be no objective, universal now that everyone agrees on.
No single present moment sweeping through time.
That's the implication. If simultaneity is relative, then the distinction between past, present, and future isn't absolute. The entire four-dimensional space-time block encompassing all events, past, present, and future, is just there. Fixed, like all the scenes on a movie reel or all the music on a CD.
And the implications of that for free will?
Well, it's not quite causal determinism in the Newtonian sense, but rather a kind of fixedness. If the future is just as real and fixed as the past, then it doesn't seem like there's much room for genuine libertarian freedom where you could truly have chosen otherwise. You're not forging the chain of events, you're just experiencing your particular path through the pre-existing block.
And this also raises questions for things like intercessory prayer, right? If the future's already fixed.
Exactly. If reality is static, how could God intervene to change future events in response to a prayer offered at a later time? It seems inconsistent with the block universe picture. Einstein himself seemed to lean this way. After his friend Michel Besso died, he wrote that famous line, "Now he has departed from this strange world a little ahead of me." That means nothing. People like us, believers in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion.
Wow. So if that's the stark picture relativity paints, are there ways thinkers try to reclaim some kind of objective flow of time, maybe even within physics itself?
Yes, there are several proposals. One approach is to be an anti-realist about spacetime itself, to argue it's just a useful mathematical tool, not a literal description of physical reality. Maybe time is more fundamental than spacetime.
Does quantum mechanics offer any help here?
Interestingly, yes. Unlike special relativity, standard quantum mechanics does seem to require or allow for absolute simultaneity, especially in phenomena like entanglement, where measuring one particle instantly affects its distant partner. This could imply an objective now that relativity seems to deny.
And historically, there were attempts like Lorentzian mechanics.
Right. Before Einstein, physicists like Hendrik Lorentz tried to explain the results of experiments like Michelson-Morley, which failed to detect the ether wind by suggesting that objects physically contract when moving through a preferred ether frame.
So that preserved a kind of absolute space and time.
It did, and it was mathematically equivalent to special relativity in its predictions. But the big problem was no one could ever detect this proposed ether. So Einstein's approach, which did away with the need for an ether altogether, became favored.
What about within general relativity, Einstein's theory of gravity? Can we find an objective cosmic time there?
In certain idealized cosmological models, specifically the Friedmann-Lemaitre-Robertson-Walker, FLRW, models that describe a uniform, expanding universe, you can define a kind of universal time. You imagine fundamental observers who are basically at rest relative to the cosmic microwave background radiation.
The leftover heat from the Big Bang.
Exactly. These observers can synchronize their clocks using signals related to the expansion, creating conceptual slices of spacetime that represent moments of absolute simultaneity across the whole universe. This is called cosmic time.
But that sounds like it depends on the universe being perfectly smooth and uniform, which it isn't really.
That's the major objection. Our actual universe is lumpy. And even theoretically, there are infinitely many ways you could mathematically slice up the space-time block into different sets of simultaneous events, different foliations. Critics argue that choosing the FLRW cosmic time as the one true time is arbitrary.
Are there newer physics approaches trying to tackle this? The book mentions things like quantum gravity.
Yes, some modern approaches like canonical quantum gravity or theories like Herjava gravity are actively trying to, in a sense, extract time from spacetime. They posit a fundamental 3+1 structure, 3 dimensions of space plus 1 of time, where time is not just another dimension like space or merely psychological, but truly fundamental. These are very much works in progress, though.
It really sounds like the philosophy of physics is unavoidable here. It's not just about the math, it's about how we interpret what the math means for reality, right?
Absolutely critical. Think about electromagnetism again. Maxwell's equations mathematically allow for both retarded solutions waves spreading out after a source emits them, which is what we see, and advanced solutions waves converging on the source before it emits them, like time running backwards.
Which seems physically impossible.
Right. So physicists simply discard the advanced solutions as non-physical. But that decision isn't purely mathematical. It's based on a philosophical commitment to causality. Koperski concludes, only one thing is absolutely clear. There is no escaping the philosophy of physics when it comes to long-standing metaphysical questions about time and freedom.
Okay, so physics gives us these incredible laws describing the universe. But for many people, especially theists, the question then becomes, how can God act in this law-governed world? Doesn't divine action mean breaking the laws? This brings us right to the problem of intervention.
It does, and it often starts with David Hume's classic definition of miracles as violations of natural laws. But if you accept that definition, you immediately run into difficult questions.
Like the problem of evil in a specific sense.
Exactly. If God can violate laws to perform a miracle, say, healing one person's tumor, then why doesn't God intervene to stop a tsunami that kills thousands or prevent other natural disasters? It makes God seem arbitrary or selective, which is theologically problematic for many.
And this fear of making God seem like a tinkerer often leads to accusations of arguing for a God the gaps.
Right, that's the pejorative term for using God to explain things science hasn't yet explained. The classic example might be, we don't know what holds atomic nuclei together, so God must be doing it supernaturally.
Until we discovered the strong nuclear force.
Exactly. Science tends to fill those gaps over time, so relying on them for evidence of God is generally seen as a losing strategy for theism. The gaps keep shrinking.
So how do different philosophical views of what laws of nature are affect this discussion?
That's crucial. Koperski outlines two main views. First, the regularity view. This says laws aren't things that govern nature. They just describe the regular patterns we observe. Like all copper conducts electricity just summarizes countless observations.
So on this view, God couldn't violate a law.
Correct, because the law isn't a thing with independent power to be violated. It's just a description of how things normally behave. God acting differently would just mean the description needs updating for that instance.
Okay, what's the alternative view?
The necessitarian view. This sees laws as having some kind of metaphysical standing or power. They genuinely govern or constrain how things can behave. On this view, it does make sense to talk about a law being violated or suspended.
And this distinction leads many non-interventionist theologians to look for ways God could act within the laws, perhaps using indeterminacy or randomness.
Precisely. If the laws themselves don't determine every single outcome, if there's some inherent randomness or slack in the system, then maybe God could influence events within those possibilities without actually breaking any laws.
And quantum mechanics seems like the obvious place to look for that randomness.
That's been the main focus, yes. Quantum mechanics famously involves probabilities. An electron's position isn't fixed until measured. A radioactive atom's decay time is unpredictable. This inherent randomness seems to provide gaps, not of ignorance, but of ontology, real indeterminacy in nature.
So the idea, called quantum determination or QD, is that God could influence, say, which way a quantum system collapses?
Exactly. When a quantum system in a superposition of states, like being in multiple places at once, interacts or is measured, its wave function is said to collapse into one definite state. Since multiple outcomes are physically possible according to the laws, the idea is God could influence which outcome occurs without violating the quantum rules themselves, like influencing a quantum dice roll to get a specific number.
Okay, that sounds potentially plausible at the micro level. But isn't there a huge challenge in getting those tiny quantum effects to make a difference in the macroscopic world we experience? The amplification problem.
That is the central difficulty for QD. Quantum effects are usually incredibly small and tend to get washed out by the thermal noise and complexity of larger systems. As Koperski quotes theologian Robert John Russell, without amplification, the effects of quantum indeterminacy do not register at the scale of our experience. A single quantum event usually doesn't change whether, say, a neuron fires or not.
Right, so this is where chaos theory enters the picture, with its famous butterfly effect, trying to bridge that scale gap.
Exactly. Chaos theory studies systems where tiny changes in initial conditions can lead to vastly different outcomes over time. The butterfly flapping its wings in Brazil, setting off a tornado in Texas, metaphorically speaking.
So the idea is, maybe God uses quantum indeterminacy, as the butterfly wing flap, to steer chaotic systems towards desired macroscopic outcomes.
That's the proposal. QD plus chaos. God influences a quantum event, which then gets amplified through a chaotic process like weather patterns or maybe even brain activity to produce a large-scale effect, all without violating any physical laws. It seems like an elegant solution.
But Koperski is critical of this, isn't he?
Yeah.
He argues that real-world chaos might not be as ubiquitous or effective an amplifier as proponents hope.
He pushes back against what he calls the argument for ubiquitous chaos. Just because many simple mathematical models exhibit chaos doesn't automatically mean most physical systems in the real world are chaotic in the right way.
What way is that?
He argues that real-world chaos is often confined to the periphery of a system's behavior and doesn't necessarily provide the kind of massive, reliable amplification needed to make quantum events routinely significant at the macro level. He uses an analogy of a child riding a tricycle. Sure, the exact path varies slightly each time, chaos on the fine scale, but the overall motion is still constrained, regularity on the large scale. The random wiggles don't usually send the tricycle flying off in a completely different direction.
So the QD plus chaos route might be a dead end, or at least not the general solution some hoped for.
It faces significant hurdles, yes. The amplification problem remains largely unsolved.
So Koperski suggests the real obstacle often assumed to block divine action isn't actually physical determinism or the lack of quantum gaps, but something more fundamental, a philosophical assumption called causal closure of the physical.
Exactly. This is the principle, or maybe assumption is a better word, that states physical effects only have physical causes. Basically, the physical world is a closed system. Nothing non-physical can influence it.
And the crucial point is that this is a metaphysical principle.
Yes. It's a philosophical stance about the nature of reality, not a direct finding of science itself. As Koperski puts it, no scientific theory demands that nature be a causally closed system. Physics describes how physical things interact, but it doesn't inherently rule out the possibility of non-physical influences.
So the old view of determinism, like maybe Spinoza's, implied laws forbade outside influence.
Right. It was seen as a completely locked system. But the modern understanding, even of deterministic laws like gravity, allows for contingency in the initial conditions.
Right.
Meaning the laws tell you what happens given a certain starting setup, but they don't necessarily dictate the setup itself. If you lift a ball off the ground, you aren't violating the law of gravity. You're just changing the initial conditions by applying an external force from your hand.
So if the universe isn't assumed to be causally closed,
then the whole search for a specific indeterministic gaps, like quantum randomness, might have been poorly motivated in the first place. If the universe is potentially an open system, then an agent outside that system, like God, hypothetically could influence its evolution by interacting with it or setting initial conditions without needing to violate the internal laws that describe how things behave within the system.
and this view has historical precedent.
Oh, yes. Newton, for example, believed God actively upheld the laws of nature and could certainly interact with the world. He wouldn't have seen a conflict there.
Okay. Now let's wade into some really controversial waters. Intelligent design, or ID. What is ID, fundamentally? And what are its main arguments according to Koperski?
ID is the position that certain features of the universe, and particularly of living things, show evidence of having been designed that they are best explained by an intelligent cause, rather than by an undirected process like Darwinian natural selection acting on random mutations.
And one of the most famous arguments is Michael Behe's irreducible complexity.
Right. Behe uses examples like the bacterial flagellum, this tiny, incredibly complex molecular motor. He argues it's irreducibly complex because if you remove any one of its many protein parts, the whole thing stops working.
Like a mousetrap.
Exactly his analogy. He argues such a system couldn't have been built up gradually by slight successive modifications, as Darwinian evolution requires, because the intermediate steps wouldn't have been functional and wouldn't have been selected for.
Okay, that's one pillar. And the other main one is William Dembski's complex specified information, or CSI.
Dembski tries to create a more general framework, not just for biology. He argues that we can reliably detect design when we find something that is both highly complex, meaning very improbable to occur by chance, like a long sequence of random letters.
And also specified.
And also specified, meaning it conforms to an independently given pattern or function. His classic example is receiving a long sequence of prime numbers from space. It's complex, unlikely to happen randomly, and specified. It matches the known pattern of primes. Dembski argues that biological information, like the sequences in DNA, exhibits CSI and claims that undirected natural processes are incapable of producing high levels of CSI. Therefore, it must be the product of intelligence.
Okay, so those are the core arguments. The immediate question that always comes up is ID actually science? Many critics say no, often pointing to the religious motivations of its proponents.
Koperski addresses this head-on. His response is basically, so what? He argues that a person's motivations for proposing an idea are irrelevant to the scientific validity or strength of the argument itself. Attacking motives is the ad hominem fallacy.
He brings up Newton again here, right?
Yeah. Yes, quoting Newton's own words from the Principia, where Newton explicitly states he had an eye upon such principles as might work with considering men for the belief of a deity. If Newton's theological motivations didn't automatically disqualify his physics as science, Koperski argues, then neither should the motivations of ID proponents disqualify their arguments from scientific consideration.
Fair enough. Another major objection, though, is that ID violates methodological naturalism, the idea that science, by definition, can only consider natural explanations.
Right. Methodological naturalism, MN, is often presented as a ground rule for science. You proceed as if only natural causes exist, even if you personally believe otherwise. Critics use MN to exclude ID because ID explicitly posits an intelligent, possibly supernatural cause.
But Koperski challenges the status of MN itself.
He argues that MN isn't some immutable axiom of science, but rather another one of those metatheoretic shaping principles, MSPs, we discussed. And like other MSPs, such as preferring simpler theories or theories with broader explanatory power, MN isn't absolute.
Meaning it can be overridden or modified.
Potentially, yes. Scientists sometimes trade off one MSP against another. For example, the standard model of particle physics is incredibly complex, sacrificing simplicity for greater explanatory power and predictive accuracy. Koperski suggests MN is often just a placeholder for other principles like testability or fruitfulness, and shouldn't be used as an unbreachable demarcation criterion.
Okay, so let's grant, for the sake of argument, that ID could be considered science in principle. The next, perhaps harder question is it good science? Does it actually succeed scientifically?
This is where Koperski thinks the case for ID is much weaker. He distinguishes between soft anomalies and hard anomalies for a scientific theory.
What's the difference?
A soft anomaly is a puzzle or a problem for the current theory, but one that could potentially be resolved within the existing framework. A hard anomaly is something that seems fundamentally incompatible with the theory, something that genuinely requires a major change or a new theory, altogether think like the discovery of black body radiation for classical physics.
And ID has produced.
Koperski argues ID has produced many soft anomalies for neo-Darwinism, pointing out genuine difficulties and unanswered questions. But, he contends, it has so far failed to produce any convincing hard ones that would necessitate abandoning the Darwinian framework in favor of design.
And there's also criticism about the ID movement's focus.
Yes, Koperski notes the relative lack of peer-reviewed scientific research coming from the ID community compared to their significant efforts in public relations and culture wars. He views this focus as a failed strategy if the goal is scientific acceptance.
He also brings up another MSP, scientific conservatism.
Right, the principle associated with philosopher W.V.O. Quine of minimal mutilation. Basically, when faced with anomalies, science prefers the theory that requires the least drastic change to our overall web of beliefs.
An ID is seen as a pretty drastic change.
Compared to other non-standard evolutionary proposals like invoking macromutations or Stephen Jay Gould's punctuated equilibrium, ID's postulation of an external designer is a much more radical departure from the existing biological framework. Koperski argues that this principle of conservatism, combined with ID's perceived lack of fruitfulness in generating new, testable research programs, is what keeps it largely on the fringes, considered fringe science by the mainstream scientific community. He's reporting on the sociological state here.
Okay, that provides a lot of context for that debate. Let's zoom out now to a broader philosophical topic that runs through a lot of science: the relationship between different layers of reality. Reductionism versus emergence. When we look at, say, a student walking across campus, is she really nothing but a collection of subatomic particles?
That's the core question, isn't it? Reductionism is the view, historically very powerful in science, that higher-level phenomena and the theories describing them can ultimately be explained by or reduced to more fundamental, lower-level entities and laws.
So psychology reduces to neuroscience, neuroscience to chemistry, chemistry to physics.
Exactly, all the way down, hypothetically, to something like quantum field theory or string theory, which would be the ground floor of reality, explaining everything else. Physics is often seen as the most fundamental science in this picture.
But this purely reductionist hypothesis faces some significant challenges,
Absolutely.
right, both from science itself and philosophy.
It certainly does. Koperski points out several. For instance, there seems to be a mismatch between the quantum world and the classical world when it comes to chaos. Standard quantum mechanics doesn't seem to allow for the kind of sensitive dependence on initial conditions that characterizes classical chaos. How does one emerge from the other? It's not obvious.
What about in biology?
Biology provides many challenges. The field of epigenetics, for example, shows that an organism's traits aren't solely determined by its DNA sequence. Environmental factors can switch genes on or off, and these changes can sometimes even be inherited. This complicates simple genetic reductionism.
And quantum mechanics itself seems to point away from pure reductionism. With entanglement.
Yes, quantum entanglement, where two particles remain linked, sharing the same fate no matter how far apart they are, suggests a kind of irreducible quantum holism. The state of the whole system, the entangled pair, cannot be fully described just by describing the states of its individual parts. Koperski suggests this points to something deeper that knits together the fabric of the world, something fundamentally non-reducible.
So this leads to alternative ideas like supervenience. where higher levels depend on lower levels, but aren't just identical to them.
Exactly. Supervenience is the idea that higher-level properties, like mental states, depend on or are determined by lower-level properties, like brain states, such that you can't have a change in the higher level without some change in the lower level. But critically, this dependence doesn't necessarily mean the higher level is reducible to or explainable solely in terms of the lower level.
But even if we accept emergence or supervenience, aren't there still tricky philosophical problems? The book mentions Jaegwon Kim's puzzles.
Yes, Kim raised some powerful challenges for non-reductive views, especially regarding mental causation. The first big one is causal redundancy, or the exclusion problem.
Okay, what's that?
If a mental state, like deciding to raise your hand, emerges from, but is distinct from, a brain state, and both the mental state and the brain state seem capable of causing the physical action, your hand going up, well, which one is doing the real causal work?
It seems like one cause is enough.
Right. If we assume the physical world is causally closed, that physical effect of the hand rising must have a sufficient physical cause in the brain, then the brain state seems to do all the work, leaving the distinct mental state with nothing to do. It becomes causally superfluous, an epiphenomenon.
Just along for the ride, but not actually steering.
Pretty much. And as Koperski notes, if mental states do not have any causal powers, then they literally cannot bring about any changes. That's a very counterintuitive position for most people.
What's the other related puzzle? Downward causation.
If you insist that the higher level mental state does cause changes in the lower level brain states, downward causation, you run into the problem of causal overdetermination. Now, you seem to have two distinct causes, the mental state and the underlying brain state, both sufficient to bring about the same effect, like the next brain state or the hand moving.
And why is that a problem?
It seems metaphysically unparsimonious, maybe even incoherent, to have two independent causes for the same event routinely happening. The scary implication of these puzzles, Kim argued, is that all real causal power might drain away down to the most fundamental level of physics, leaving all higher levels, chemistry, biology, psychology, causally inert.
That's a pretty bleak picture. Does physics itself offer a different perspective? Maybe one that doesn't think in such strict levels?
Koperski suggests it does. Physics often deals with complex realities in ways that don't fit a neat hierarchical reductionist model. Physicists talk about nested and entangled systems, where the behavior of the whole influences the parts, and often ignore micro details to focus on collective behavior.
Like the convection cells example.
Exactly. When water boils, those rolling convection cells emerge. Their behavior isn't just determined by the interactions of individual water molecules at the bottom. It also depends crucially on non-local factors, like the temperature difference between the top and bottom surfaces, the shape of the container, and gravity. The larger context shapes the microbehavior.
And feels like fluid dynamics seem to work without reducing everything to particles.
Right. Fluid dynamics or continuum mechanics successfully model things like airflow over a wing or the bending of a steel beam by treating the material essentially as a continuous substance, ignoring its actual discrete molecular nature. This works because the macroscopic behavior often doesn't depend sensitively on the precise arrangement of every single molecule.
There are mathematical relationships that capture this.
Yes, Koperski mentions constitutive relations, mathematical equations used in continuum mechanics that describe how stress or heat flows through a material. Crucially, defining these relations often requires information that comes from sources other than the material base itself, things like boundary conditions or overall system properties.
So the upshot is that reductionism isn't the whole story, even within physics. There's a case for emergence having equal standing.
That's the argument. Parity between reduction and emergence, with both finding support within scientific practice itself.
And this view of emergence then becomes appealing for theology.
Yes, particularly for theists looking for ways God might interact with the world holistically. Some theologians, like Arthur Peacock, envision God acting top-down on the whole of creation, influencing the boundary conditions or overall state of the universe, which then shapes events within it, somewhat analogous to how those non-local factors influence convection cells.
Though Koperski adds a note of caution.
Yes, he notes these theological applications can sometimes be vague and might rely on an overly simplistic hierarchical picture of levels that physics itself doesn't always adhere to, but the potential connection is there.
Okay, as we head towards the end of our deep dive, let's open up the philosopher's toolbox, as Koperski does, and look at some big conceptual tools for understanding science and its relation to these issues. First up, Realism versus anti-realism in science.
A fundamental debate in philosophy of science.
Scientific realism is kind of the default intuitive view, isn't it? That our best mature scientific theories are actually true, or at least approximately true, and that the unobservable things they talk about, electrons, quarks, black holes, genuinely exist.
Exactly. The main argument for realism is the no miracles argument. It would be an absolute miracle if our theories work so incredibly well, allowing us to build lasers, predict planetary motions with stunning accuracy, develop medicines if they weren't actually latching on to the real structure of the world. Their success would be inexplicable otherwise.
But anti-realism pushes back hard against this intuition. What are some of the main challenges?
One big one is the pessimistic meta-induction, or the argument from the success of false theories. History is littered with scientific theories that were once incredibly successful, they explained a lot, made good predictions, but which we now believe are fundamentally false. Think of caloric theory for heat, phlogiston for combustion, even Newtonian gravity, superseded by Einstein. If all those successful theories turned out to be wrong, why should we assume our current best theories are true? Maybe they're just useful fictions destined for the historical scrap heap too.
That's a sobering thought for scientists. What about underdetermination?
This is the argument that the available empirical evidence often, maybe always, logically underdetermines theory choice. That means there could be other, completely different theories that are equally comparable with all the data we have.
Unconceived alternatives, as the book calls them.
Right. Even if we don't have a specific rival theory right now, how do we know there isn't one out there that explains the data just as well, but posits totally different, unobservable entities or laws? This leads some anti-realists towards instrumentalism. Theories are just useful tools for prediction. Truth is irrelevant. Or constructive empiricism. We should be realists about observable things, but remain agnostic about unobservable theoretical entities.
And Thomas Kuhn's work on paradigms added another layer of complexity.
Hugely influential. Kuhn argued that scientists always work within a paradigm, a whole set of shared assumptions, methods, and even ways of seeing the world. He claimed that paradigms aren't directly comparable, and that when a scientific revolution happens, like the shift from Newtonian to Einsteinian physics, scientists working in the new paradigm literally saw a different world. There's no neutral, paradigm-free viewpoint from which to judge which theory is closer to the absolute truth.
Which leads to the most extreme view, social constructivism.
Yes, the idea that scientific knowledge isn't objective truth about a mind-independent reality at all, but is entirely a product of social negotiations, power structures, and cultural biases. Reality itself is seen as socially constructed.
That's a pretty radical departure from realism. Yet Koperski notes most scientists and philosophers remain realists of some kind, maybe a more nuanced realism.
Yes, the no miracles argument for realism still carries a lot of weight for many, but it's often tempered into a more cautious local realism rather than a global sweeping claim that all of mature science is true. It acknowledges the fragmentation of science, physics, biology, psychology don't always connect seamlessly. Koperski emphasizes that science often does not make progress in a smooth, linear way. Advances come piecemeal. We need to accept the messiness and internal tensions.
And the concept of models in science seems really relevant here. Science uses models all the time that aren't meant to be perfectly realistic, right?
Absolutely. Models are crucial scientific tools. They are representations, but often deliberately simplified ones, not considered fully realistic. Think of physicists using models of frictionless planes or point masses. These are useful fictions that allow calculations or highlight certain aspects of a phenomenon. Sometimes models are used simply because we lack a complete underlying theory. These are phenomenological models.
And Koperski suggests this idea of using models could be helpful in theology too.
He does. He proposes that some long-standing theological disputes could perhaps be better understood not as conflicts between competing claims to absolute doctrinal truth, but as a conflict of models.
Like different ways of picturing God or salvation.
Exactly. He uses John Polkinghorne's example. Is it better to model God as a personal father, or as an impersonal cosmic force? Or consider the different theories of atonement, Christ's death paying a penalty versus defeating evil powers versus demonstrating love. Maybe, Koperski suggests, these aren't mutually exclusive doctrines, but different complementary models, each capturing some aspect of a deeper truth. Having a portfolio of useful models might be more fruitful than insisting on one literal description.
That's an interesting perspective. Now, we often hear science contrasted with religion by saying science relies on reason, while religion relies on faith. But Koperski unpacks what reason in science actually involves, and it's not always simple deduction.
Right. Science employs various forms of reasoning. One of the most important, especially in theory choice or positing unobservables, is inference to the best explanation, or IBE. Yeah. It's the process where, faced with some data, you consider several possible explanations, and you infer that the one which provides the best explanation is likely true, or at least the most reasonable one to accept. It's not logically airtight deduction, but it's a fundamental way we reason.
And it's used everywhere, not just science.
Oh, yeah. A mechanic diagnosing engine trouble, a detective solving a crime, a historian interpreting ancient texts, they all use IBE constantly. Scientists use it to argue for theories, like evolution providing the best explanation for the fossil record, or for the existence of entities, like electrons being the best explanation for tracks in a cloud chamber.
But what counts as the best explanation can be tricky.
That's the philosophical challenge. Scientists appeal to explanatory virtues like simplicity, scope, explaining more data, coherence with other theories, predictive power, clarity. But are these virtues? Definitely. Theories aren't and shouldn't be abandoned at the first sign of trouble, tenacity. And changes to established theories tend to happen incrementally, preserving as much of the old framework as possible, conservatism. Scientific revolutions are the exception, not the rule. The messy, decades-long development of quantum mechanics is a prime example. Classical ideas were tweaked and patched long before being fully overthrown.
Finally, let's touch on the limits of knowledge and the idea of mystery, both in science and theology. Science hasn't solved everything, has it?
Far from it. Koperski points to persistent, deep puzzles within physics itself. The measurement problem in quantum mechanics, what really happens during collapse, how classical chaos emerges from quantum foundations, the nature of dark matter and dark energy, and in cosmology, the Big Bang singularity itself, the point where our best theory, general relativity, simply breaks down and gives nonsensical answers.
So science acknowledges its limits.
Good science does. It seems likely that some corners of nature will remain at least partially shrouded in mystery, perhaps due to fundamental limits on our ability to probe or comprehend them.
And this, Koperski suggests, can help us put the concept of mystery in theology into perspective.
Yes. In theology, mystery typically refers to truths, like the Trinity or the Incarnation, that are considered beyond full human comprehension and, if known at all, must be revealed by God. They bridge an epistemic gap between the finite human mind and the infinite or supernatural.
Critics often dismiss this as just a convenient cop-out when explanations fail.
They do. But Koperski's point is that if even science, with its powerful empirical methods, runs into apparent limits and conceptual singularities, maybe we shouldn't be so quick to dismiss the possibility of genuine mysteries in the theological realm.
He offers the Trinity as a potential analogy to a scientific singularity.
It's a fascinating suggestion. He frames the doctrine of the Trinity, three distinct persons, Father, Son, Holy Spirit, who are nonetheless one single God, as a kind of singularity of monotheism and personhood. Meaning, monotheism and personhood are both concepts that work reasonably well on their own. But when you try to combine them in the specific way the doctrine of the Trinity does, our standard conceptual frameworks are stretched to their absolute breaking point, much like space-time concepts break down at a black hole singularity.
So it doesn't necessarily mean the doctrine is false, but that our models fail.
Exactly. It highlights the limits of our human conceptual models when trying to grasp something potentially transcendent. Of course, this raises the crucial question. One might ask, if the appeal to mystery is not a blank check, under what conditions can it be used?
It can't just be used anytime something is difficult.
Right. Koperski suggests it involves careful trade-offs between theological shaping principles, balancing fidelity to scripture or tradition against principles like coherence, simplicity, and explanatory power within the theological system itself. It's not arbitrary.
Wow. This deep dive has truly mapped out some incredible territory, revealing just how surprisingly intricate and deeply interconnected the worlds of science, philosophy, and religious belief really are.
It definitely shows it's far more complex and I think more dynamic than those simple narratives of just conflict or just complete separation that you often hear.
Understanding these relationships, and especially recognizing the role of those underlying meta-theoretic shaping principles, really does help you navigate this complex intellectual landscape. It feels like we've got a much better map now.
I think so. And it underscores, doesn't it, that knowledge, whether it's scientific, philosophical, or theological, is ultimately a human enterprise. It's shaped by history, by assumptions, by different forms of reasoning.
And even with our best methods, our most powerful theories, there are still horizons, still limits to what we can fully grasp.
Absolutely. Limits, mysteries, singularities, they seem to be part of the landscape in all these domains.
So here's a final thought to leave you with. If scientists, with all their sophisticated experiments, powerful mathematics, and rigorous methods, still face fundamental limits and persistent mysteries about the nature of reality, what does that mean for how you approach questions of truth, certainty, and belief in other areas of your life?